the other interpretation that we will see now, which is actually very useful for the task of conditional generation, is DDPM as score predictors. So this interpretation also has a very strong relationship between what are called as the score based models. So we'll see what that is. Okay, now there is suppose there is a famous result in classical statistics that says the following. Suppose t is a random variable that is Gaussian, okay, and let's say the mean of this Gaussian distribution is mu t and the variance is sigma t. Then there is something called Tweedy's formula. This is a known result in statistics that would say that the conditional expectation of the mean given the random variable, given that we have observed the random variable t, is given by the observed value of the random variable plus the variance times the score vector t log p of t, okay, where pt is the distribution from which we are sampling t, which is the normal distribution in this case. So now this is what we call as p of t. Now I will not prove this result, I will take this as a fact. So what this is saying is, suppose there is a Gaussian random variable with a certain mean and variance. If you want to compute the expected value of the mean vector, given that you have already observed a particular value of the random variable, then it is given by this particular formula, where the gradient of the log of a particular distribution with respect to the underlying random variable is defined as the score function. Okay, see now look at this. Typically we take the log likelihood of a given distribution, and the derivatives are computed with respect to model parameters, right? So here the gradients are being computed with respect to the random variable upon which the distribution is supported, right? So score of a given distribution is the gradient or the derivative of the log likelihood of the density function with respect to the random variable itself upon which the distribution is supported. So that is the definition of the score function. Okay, now why is this of importance to us? So intuitively, what is the score function telling you? The score function tells us what is the direction, okay, in which the log likelihood is peaking. So suppose you want to find a model that would maximize the log likelihood. So what one should do is that traverse in the direction where the score function points, because score function is telling us what is the rate of the change of the log likelihood of the density function with respect to random variable. So we are saying in the space of the random variables, the range of the random variables, which is the direction along which one needs to traverse, is what is pointed out. I mean, so that we match the true distribution is what is being pointed out by the score of the distribution. So score of the distribution is simply the gradient of the log likelihood of the distribution with respect to the random variable itself. Okay. Now why is this of importance in the current context is, so now you recall in the case of a DDPM, that in a DDPM the distribution of the tth latent variable or the noise vector conditioned on the input is given by a normal distribution, right? This we have derived this xt, and the mean is given by square root of alpha bar times x naught, and the variance is 1 minus alpha t bar times the identity matrix. Okay, so this we have derived. So now if we apply the TD's formula to this, formula to above, we have the expectation of the mean given xt, the random variable that we are talking about is xt now, is given by xt plus 1 minus alpha t bar times the score. The score is log of the distribution that we are talking about. This is p of xt, and the derivative is with respect to xt, right? So the derivative is with respect to xt now. Okay, now we also know that suppose you have one particular sample. Okay, suppose the best estimate for the conditional mean, which is the expected value of mu given xt, is the true mean itself. See, if we know what the exact true mean is, the best estimate is the true mean. The true mean itself is the best estimate, which implies that the expectation of mu given xt is the mean of this distribution, which is this one. Okay, which is root of alpha t bar times x naught. Now if I plug this into the TD's formula, so my root of alpha t bar times x naught, which is the LHS, is now equal to xt plus 1 minus alpha t bar times the score function, the marginal distribution of xt. So p of xt, we will define what log of p of xt is in a while in the context of a DDPM. So this is just application of the TD's formula. Now rearranging the terms, if we rearrange the terms here, I can write x naught in terms of xt and the score function times the derivative of log of p of xt, which is the score function with respect to xt, divided by, this is just rearranged in the terms and in the algebra, this will be alpha t bar. So now what did I do? Just using the result in statistics, which is the TD's formula, we just expressed the true data x naught in terms of xt, which is the thth latent variable, and what is called as the score function. Okay, now why is this of importance? As usual, we can rewrite the consistency term in our loss function, the elbow, in terms of xt and the score function. That is the equivalent interpretation that we have. So now expressing the consistency term in terms of scores, in terms of score functions. Now recall that our mu q, which is a function of xt and x naught, which is what we had in the consistency term, is given by root of alpha t. Maybe I can just copy it to avoid writing it again. This was the definition of mu q that appears in the consistency term. Now here I just replace x naught by this particular expression. So x naught, we wrote down x naught in terms of xt and the score function. I can simply write down x naught in terms of xt and the score function, which we have just derived using the 2D's formula. So this is xt, x naught. Okay, so this will be our x naught. Using the result above. So that is what we do. So now again I will skip the algebra. If you rearrange the terms, finally this will be 1 by root of alpha t times xt plus 1 minus alpha t divided by root of alpha t times the score function log p of xt with respect to xt. So this is my mu q now. Okay. So now mu q is represented in terms of xt and the score function. Okay. Now once we do that, we know what the next trick is. We'll write down the mu theta similarly in terms of mu q. So this can be written as similarly in the lines of mu q. This is 1 by alpha t times xt plus, and as I keep saying, the same trick will subsume all the constants and put everything in the neural network. I'll write this as s theta, just take xt. So now where s theta of xt is the predicted score using neural networks. So this is another interpretation. So now what happens is, with this, the consistency term, which was the norm of the difference between mu q and mu theta, can be represented in terms of all the, well, just skipping all the constants, the difference between the true score and predicted score. Okay, this is another interpretation. Now we will write down the exact same structure that we had. So now this is the third or rather fourth interpretation of what we are doing in a DDPM. So the same DDPM can be again looked into as regression over the score of the distribution. This is regression over the score function. So now this neural network takes xt and t as input, and what does it predict? It predicts the score of the distribution so regression over the score function, so regressor on the score function. This is the third interpretation. Okay. Now one might ask this question. I mean, in all the other interpretation, we knew what the true data point was, or true mean was, or the true noise, added noise was, so that we could regress upon, right? So now here, S theta of xt is the output of the neural network, fine, but how do we know what the true score is? Right? So we don't know what the true score is. So it turns out that we know what true score is. So let us write that down. So to compute the true score, so you might have already seen how to compute the true score. So we had this definition, right? X naught was given by xt using the Tweedy's formula. What did we write? This was epsilon 1 minus epsilon times the score root of x log of pxt divided by root of alpha t, right? This is what we saw using the Tweedy's formula. But we also know that this is equal to x naught is also equal to, also we have x naught is equal to xt minus root of 1 minus alpha t bar times epsilon t divided by root of alpha t bar, right? So this is by definition, right? This is by definition. And we have epsilon t is the noise that we added to x naught to make it xt. So that is by definition. So equating 1 and 2, if you simply equate this 1 and 2, this we'll call as equation 2. So now equating 1 and 2, it's very easy to see that the score, equating 1 and 2 and rearranging, I'll just skip the algebra. So I'm deliberately skipping the algebra and leaving it as an exercise because it will consume a lot more time, and it's pretty easy to do the algebra. I leave it as an exercise to students. So now the true score that we seek is simply equal to 1 negative of 1 by root of 1 minus alpha t bar times epsilon t. Okay, so now this is a very elegant result which is showing that true score is simply the negatively scaled noise. So that's it. Now what we are saying is higher the noise, lower the score, and vice versa. I mean, it's obvious, right? Because suppose you take an x naught and add some noise. Now the score function should point in the direction that is opposite to that of noise, because if one were to traverse from the noisy point to the point where the distribution peaks, which is the no noise point, you will have to traverse in the direction that is exactly opposite to that of noise, right? So that's why the true score is nothing but the scaled version of the negatively scaled version of the noise. Okay, now what does this mean? This also means, this implies that a DDPM trained to regress over noise. Okay, one of the interpretations that we just saw was that it is regressing over the added noise. Okay, I'll just call it as added noise. Added noise is implicitly predicting the score. Implicitly predicting the score function. So this is the bottom line. Okay, so now whenever we talk of DDPM, so we can talk of three different interpretations. One, that given xt, so note that in all of these interpretations, right, the input is always xt comma t, so it is taking xt and t as the input. Now given xt and t, the neural network either can be looked into as predicting what the true data point x naught is, or it can be looked into as predicting what the mean mu theta is, or it can be looked into as predicting epsilon t, which is the added noise, or it can be interpreted as predicting the score. So depending upon what your loss function is, right? I mean, if you regress over the added noise, then you can interpret this neural network as regress over noise. And if your loss function is x t minus x naught, then it is regression over the true data point. And if it is mu q minus mu theta, then it is regression over the mean. And if it's s theta minus the score, then it is regression over score, and so on. So it does not matter what one is interpreting it as. The underlying and all the loss functions that we talked of are simply the scaled and shifted versions of each other, so it does not matter. The neural network is learning the exact same thing irrespective of the interpretation that one has. Okay, so now the bottom line is that all these neural networks are exactly equivalent. Okay, and the most used interpretation of a DDPM is that of regressor over noise. So it takes xt and t as an input, and what it predicts is the epsilon t, which was the noise that was added to x naught to make it xt. So let us keep this interpretation for our further discussions. But this is a very important point, that the DDPM or the neural network that is designed to regress over the added noise is also regressing over the score function. Okay, so now this implies that whatever analysis that we do on noise, using the predictor as noise, can be done by taking the score functions and vice versa. Okay, this is a very important point, because when we have to convert our DDPMs for conditional sampling, we will be using this result, that we will be interpreting this DDPM or the neural network that we use for DDPM as a regressor over the score function, because it is easier to do it that way. So whenever I am saying that we are regressing over score function, we are implicitly regressing over the added noise and vice versa. So just have to keep that in mind.